the remaining time to quickly go over the task, and the exam sheet is in like that. So we'll look at this one. For this question, we learn how to draw the shear and Mement diagram, and then this one we can apply to so for this case, we simply apply the exercise. So now we have the formula we know is dv dx equal to minus omega, and dm dx equal to v. And sign conventions we have is here. This for positive, and that's sections. And also for omega, this is the beam. The downward omega for this case is positive, so that is our sign convention. The first step for this problem is we have to solve for the reference force and the support here. And this one, the reference force, we can apply the equilibrium equation, so we can, that is about a few minutes, you can solve for the two values in the newtons. So everything is starting from here, and for these questions, here you can see in particular, the loading we applied is kind of the, apply the hammer and then try to do this. So we want to convert this loading, which means multiply this loading by distance and convert it into a loading that is equivalent to this point here. That is F equal to 3 kilonewtons, and also this loading multiplied with this arm will produce a bending. Okay, so, and that is a skip. We try to get everything onto this line here, and this bending will be equal to 3 multiplied with 0.9 is 2.7 kilonewton meter. Okay, so in this way, let me get rid of this one. So, for example, with that conversion, so we don't have to care about this conversion. We simply look at the distribution of the red color and the W. So starting from here, that is our starting point, and per our sign convention, the 6.5 applied to this cross section, that should be positive. We're starting from here. And now in this range, we have the omega equal to constant, so that means meaning the slope of this V curve is equal to minus omega, so that means in this range, the slope equal to minus 3.5. So we're starting from 6.75 and taking the slope minus 3.5, and that will be like this. Okay, and the value we can calculate should be up, right?
Yeah, it's 1.5.
Should be up. Let me see. 3.5 times 1.5, that is 3.5, 1.75, 5.25. So that should be here.
straight line at 5.25?
Should be like this, right? Okay, and then this value, this value here is 1.5. Here. And then again, to this range, it continue. Go to here. Okay. And then this is 0.9, 0.9 times 3.5, 0.9 times 3. So right now I'm trying to calculate what is the value here. This value is 1.5, and the slope equal to minus 3.5. The slope is the same, 3.5. So here we can calculate the descending here. So the distance from here to here, that is 3.5 times 0.9, and that is 31.5, 3.15. Okay, so the descending from this point to here is 3.15. So that means this value will be equal to how much?
Negative 1.65.
Negative 1.65. Okay. And now, okay. So now we come to this point, and at this point we have 3 kilonewton point downward. So that means that will contribute a discontinuity that is downward. So that is downward by how much? By 3. So that means the distance from here to here will be 3. Okay, so that means come to this point is minus 4.65. Okay, this 3 because of this force here. And again, for those things, you can use the free body diagram and piece by piece working through. But here I directly apply the formula, so we directly work on these things. And one more time, if you're not sure why we have this one, and again, for your practice, you simply apply the free body diagrams and working piece by piece, segment by segment, and through this way to verify the application of the two formulas. Okay? And now we come to here. And then to this in this range, and again, we have the omega, so that means we have the same descending. That means in this range, dv dx equal to minus omega, so the slope equal to minus 3.5, so that means here. And for this case, this is 3.5, the slope. And so that means here the distance. So from here to here, that descending is 3.5 multiplied with 0.6. And that is 5, 7, 2.1. So that means here we have the value is, this value is minus 6.75 here. And then to 6.5, again we have the upwarding, loading, so that will go up by this amount. So we come to here exactly equal to 0. From here you can see this is the free surface that with the any other loading, so that will stop at 0 here. So this provides us a checking point for building up the curve. Okay?
When will your shear not be 0? If those
Sorry. I think here the shear, let me repeat. The shear at this end should be this magnitude 6.75. Yeah, so basically is here. Okay. So basically here we know that this amount, we obtain this amount is propagated from the information from here to this end. And then to this end, we know that this end is a boundary condition must match the given information, and we check that information. We calculate it from propagation from there to here, and then we check against this information. Any other questions? And now we work on the M. So here this has no moment, so M should start from here. And so M starts from here, and then we can see the M equal to V. So for this case, we can see the M will be V times dx integral. So for this case, we don't need to integrate. If you wish, you can integrate this equation exactly. For example, you can find out what is a V for this case. So for example, the Vx, you can formulate, etc., and plug in the V of the function x into here. But here, for drawing this kind of things, we can ignore, we can skip this detailed calculation by doing this. By doing what? V is the function, let me use the symbol. V is a function of the x to the first power, so which means that's a straight line. So this straight line, after integrations, will give us the second power, which means hyperbolic. Okay. So this is a hyperbolic curve. We know that when we draw, this should be the portion of a hyperbolic. And hyperbolic, we have the couple things here, either this one or either this one. Right? So right now we identify this is hyperbolic, and then we have to determine which piece. Okay, and the piece is this. For this case, you can see the slope of the moment equal to V. V is decreasing from more positive to less positive. Okay? The V is decreasing from more positive to less positive. But here we're looking for the positive slope. Where is more positive? So here, this point has the slope. This one you can see that is very positive. And to this point here is getting less positive, and until here is getting to 0. So this portion is what we are looking for. The point when we trace the point, the curve here, and then you can see along with our tracing, then the changing in the slope on each point actually fitting into this train. So here we have to draw is something like this, arbitrarily. Okay? Or otherwise, if you don't believe this one, then you can simply formulate. So this is the schematic, and how about let me show you the detailed way. Or you can try is this, the dm dx. In the first segment, let me formulate the function here. So here in the first segment is Vx will be equal to 67.5. Let me write it up here to here. So let me call this the first segment. In the first segment is V1 x. To look at that equation, that is 6.75 minus 3.5x. Okay, so if we want to do the detailed calculation, we do this way. Then m will be equal to 6.75 minus 3.5x and dx. Integration is from 0 to x equal to 1.5. So x equal to 0 to 1.5. So we integrate this one, to whatever. Okay, so basically that is 7.5x minus 3.5x squared. This equation is this one. Okay, so let me finish this one. So at this point, the slope on the M curve equal to value of V. So at this point, the slope still a little bit positive, not straight. Okay, and then to here, extending to here, and corresponding to this point here, the value of v equal to 0, the value of v equal to 0, that means at this point, the slope of m should be equal to 0. So this point should be the peak of the n curve. Okay? When I work on this one, I have no time to watch your face, so you have to take it yourself. Okay? So here again, you can see when x at this position, the value of v equal to 0. When value of v equal to 0, that means the slope of m at there equal to 0. So that means the slope at here should be horizontal here. Okay. Or otherwise, if you implement these equations, once you have this equation, you have to draw the point, the curve on here. Then you simply carefully make a few points and you trace the point, and you will get the same thing. Okay. And now come to here. Now come to here beyond, now we continue, this will be peak and then descending, begin to descend a little bit to here. Okay. So, at least here, the slope equal to 0 here. Okay, that corresponding is this point. And exactly, if I will ask you, what is the position here? What is this position? Let me call it S star. Then that position you need to work out is using this triangle, right? That triangle basically tell us is this one, and the height equal to 1.5. The descending is 3.5. So that means what is this distance? 1.5 divided by 3.5. That is 3 over 7. 3 over 7, I think, is point 4.3, about 4.3. Okay, so that means that x bar, these positions will be equal to 1.5 plus 4.3, that is 1.5 plus 0.43. That is equal to 1.93. So that means the maximum bending occurs around this position, around here. So that position exactly is measured 1.93 meters from the left angle. From here we can exactly calculate where is the maximum bending. Okay, now we proceed. And now to this point, and now we want to get over this position. At this position we have this bending applied. So that bending applied, that will be ambiguous. So we can work on the free body diagram. Again, if we are not sure what we are doing using the two equations, the most straightforward way is to use free body diagram. So I draw the free body diagram. Right now I pick out a section. That section just cross this point, and that is a portion of the free body diagram I pick. And that is sections I expose. And then we can draw the loading. The loading here we applied has the distributed loading here. And say here, because I picked this section, is just over the point, just over this point. So I would say the whole length will be equal to 1.5 plus 0.9 equal to 2.4. Okay? Because I just want to know what is the influence of this bending to the change of the curve here. We know that because the bending here externally applied, we expect they should have a discontinuity, either down or up. We don't know yet, but I don't know how to do it. So here we draw the free body diagram. And on the free body diagram, we also have the loading here. Here is 3 kilonewtons, and also here we have the bending. That is 3.7 kilonewton meter. And now from here, I want to calculate is the direction force and moment. So let me say direction force on this section will be V and will be M like this. Okay. Here this